This work was done in the context of PROMISE project, work package 3, demonstrating solution for zero pollution for material cycle and soil groundwater continuum, within the framework of REMTECH thesis, which aim is the development of an on-site treatment process for PFAS degradation mechanism and kinetics. The investigated PFAS is the target PFAS is the perfluorooctanoic acid (PFOA), which is known as a carcinogenic to humans since 2023. So it has both human and environmental health concerns. She's hydrophobic due to the 8-carbon backbone and hydrophilic in agreement with the COH function. It is very soluble in water in up to 8.5 grams per liter. Its pH is under 0.5, so it is under an anaerobic form in the range from the pH range from 1 to 40. It is he has a high chemical stability due to the cell bond, and it has a high thermal stability. Let us note that its boiling point reaches 190. When regarding bibliography, we saw that Trangetol in 2022 investigated the PFOA degradation using DMSO and NaOH mixture under moderate thermal treatment. They use OH- as a nucleophile. So more you increase the pH, more the OH- is active as a nucleophile. And they use also DMSO, which is a polar aquatic solvent, which boiling point is 189 degrees Celsius. So the use of a polar aquatic solvent increases the nucleophilicity of OH-. It also increases the range of temperature heat treatment, so it can increase the number of effective collisions between the mixture and the analyte. So by investigating PFOA, DMSO and NaOH at 120 degrees Celsius, they demonstrated that perfluoroalkyl carboxylic acid they chlorinated using a loop. So first of all, you have your acid, which is acetate. Then temperature is able to remove CO2, such as the intermediate one is an anionic. The anions, the doublet make a double bond, such as you remove one F- to have the intermediate 2, and OH- react with the intermediate 2, such as to have the intermediate 4, and intermediate 4, because you are under alkaline condition, the OH is O-, and the doublet of O push away the double bond to the less carbon, such as you have intermediate 6. And then OH- is also now able to interact within the COA, such as to have a COOH at the end of the molecule. And then the cycle is repeated various times, such as you have a mass balance at the end of the experiment, such as the fluoride. 18% of the fluor content is under fluoride, and TFA, which is the trifluoroacetate, which is there. And then the total carbon is under format, carbonate, oxalate, nicolate, and TFA. So that is a promising process for on-site treatment of PFAS. But what we decided is to investigate and optimize the PFOA defluorination using DMSO and NaOH mixture under moderate thermal treatment for on-site treatment. And we decided to optimize the DMSO H2O volume ratio in the range from 1:8 to 8:1. We also investigated the NaOH PFOA molar ratio in the range from 5:1 and 31:1 at 120 and in the range from 0 to 144 hours. Experiments were conducted in vials of 20 milliliters. We used 5.6 milliliters of solution in total, and the total concentration of PFOA was 0.893 per liter, and the total F content was 690 milligrams per liter. To analyze the procedure, so we use liquid chromatography with ultra high pressure chain coupled to mass spectrometer, LCMS, for the analysis of PFOA and byproducts, and the analysis range, the PFAS analysis ranges from 1 nanogram per liter to 5,000 nanogram per liter. And we use also potentiometry using fluoride ion selective electrode for F- measurement. And that's for F-, we are able to analyze it, quantify it in the range from 20 microgram per liter to 20 milligram per liter. So under the investigated condition, first, it means the conditions are there during 140 hours. What we saw is that we can see here the relative evolution of the PFOA content versus time, and also the relative evolution of F- content versus time. And what we see that PFOA has a first order reaction. It is removed. It is removed versus time, and PFOA is under the limit of quantitation, 0.3 nanogram per liter, after 6 hours. But there is only 80% of defluorination of PFOA and byproducts after 18 hours. So it's okay. The validation of the defluorination process is okay. It was compared by SEM and EDS analysis when we analyzed 20 microliter of dry PFOA DMSO and NaOH mixture. So here you can see the NAF crystal structure that we determine, NAF crystal. So, okay, the process worked, let's optimize it. And when we analyze the influence of the DMSO OH volume ratio, and we analyze the relative PFOA removal, and at the same time the relative fluoride content, what we see is that there is a perfect removal for the DMSO H2O volume ratio ranging from 4:1 to 2:1, then it decreases progressively. Okay, and when we regard the relative fluoride content, we see that for 8:1 and 4:1 volume ratio, it reached 80% and it decreased when the volume of water increased. So what we have is water is responsible for the inhibition of PFOA defluorination. Indeed, OH noise hydration decreases the OH nucleophilicity. Then we perform experiments regarding NaOH PFOA molar ratio, And what we saw is that whatever the investigated NaOH PFOA molar ratio from 31:1 to 5:1, the PFOA content, which is under the limits of quantification, whatever the OH content. Whereas when we are looking for fluoride content, which is the maximum of fluoride of defluorination reached 80%, and then it decreased when we decrease the OH minus ratio. So okay for the nucleophile degradation, but for a lower ratio, there is not enough OH minus, which is also involved into the CO2 acidobatic reaction, which consume OH minus, and which is also involved in the OH hydration that decrease the nucleophilicity. Regarding the optimization of PFOA defluorination under the investigated condition, we see that we can use DMSO water volume ratio ranging from 4:1 to 8.1. Regarding the NaOH PFOA ratio, we can range it from 21:1 to 31:1. There is nucleophile degradation. There is a total removal of PFOA, but there is also 80% of defluorination. That is quite good, but there is occurrence of persistent degradation products, and according to Trangetal, it's possibly TFA. So let's investigate the mechanism. And here are represented the relative evolution of PFOA and the byproduct versus time. So these are the products that we are able to analyze at laboratory. And what you see is that there is production and disappearance of PFOA byproducts. So TFA, and in a lesser extent, PFOA and PRA, which are those molecules, are the main byproducts that decrease versus time until TFA and PFOA concentration reach a concentration under the limit of detection, and PFPRA reach the limit of quantitation. So that was the first disagreement with Trangetal. But those and this product, PFPRA, only accounts for 0.27% of the total fluoride. So there is occurrence of persistent degradation products that we investigated. And according to literature, we investigated the relative area of 325, 275, 229, 225 MSZ byproducts. So we identified them, and here are the relative areas. So they increase, decrease, increase again, for decreasing until reaching zero, but not zero. So we have to quantify them. This is really, really important. What we also see, that was a nice investigation, because we are, with those molecules, validating the defluorination mechanism proposed by Trangetal using calculations.